All right, in this lesson we are going to begin to discuss the curvature. And the purpose of this is we have to make good on teasing apart the Einstein equation. You remember the Einstein equation is the Einstein tensor being equated to 8 pi times the stress energy tensor. And we've put this guy on hold for a while because we're working in the vacuum where that will ultimately be 0 for vacuum solutions. But it's this guy that is important. And the Einstein tensor has the definition of being the Ricci tensor minus 1/2 of the metric tensor multiplied by the curvature. And then to understand what those things are, we blow this guy up and we realize this guy, the Ricci tensor, is the contraction of this tensor, a 1-3 rank tensor. And that guy is the curvature tensor. This guy here. This guy is the contraction of the Ricci tensor. So here, this is going to be R, say, alpha, well, let's see, R beta alpha G alpha beta. So then we'll have minus 1/2 G mu nu. And this will take beta, raise it, make it alpha alpha, and then that'll be a single number. And then there are our leftover indices which match the mu nu, mu nu, mu nu. These leave mu nu behind. So all of this flows, and then of course this guy right here, just as with this comes from our beta, say, delta alpha delta. So again, we always end up at this curvature tensor here. So the curvature tensor flows all the way through this into the Einstein equation. And so we have to understand the curvature tensor. But once you understand the curvature tensor, the rest of it kind of falls into line. There's the question of interpreting things, which we'll try to work on a little bit. But we're going to begin with sort of the basic definition of how this object is constructed in a formal way, and then we'll move to the intuitive way, which is counter how normal things do. Normal books try to squeeze it in with intuition first and then get increasingly formal, but if you want that approach, just read literally any book in the subject. We're going to go ahead and play around with the formal notation, the formal definition, and then try to work back and attack some of the intuition. So let's begin. Why don't we go back and look at how we defined the torsion? Because we did the same thing with the torsion. We started with a very formal definition, and then we worked back to try to figure out some kind of intuitive understanding. But when we talked about the torsion, we talked about the torsion as a map. And it took a map from this Cartesian product space, the Cartesian product space of vector fields on a spacetime. So the dual Cartesian product, or the double Cartesian product, or I don't know, how do you put it? The Cartesian well, I guess it's just a product of two things, right? As I'm worried about, in a moment, we're going to do a Cartesian product that has 3 sets. But we'll just call this the Cartesian product of the set of vector fields on a spacetime, but the mapping delivers us another vector field on the spacetime. So what this guy here is supposed to mean, as a review, is S is the spacetime. So S is what we're using to model the entire physical situation, which is the spacetime. So we know that we have four coordinates, and every point is labeled by 4 coordinates, which is sometimes just written as x, or sometimes is written as x alpha with a little subscript up there to indicate there's 4. It goes many different ways in many different books, but every point will have those 4 coordinates. So and then this chi represents the set of all vector fields. So the vector fields are going to be objects that have some sort of basis, and in the coordinate basis it would be del with the single subscript, and then x alpha, and x alpha del would be a vector field, and this is to be understood as x alpha as a function on the spacetime del alpha. right? And so this component of the vector field is a function on the spacetime. That's why it is a field. If that wasn't the case, it would just be a vector at one particular point. If I wrote x alpha partial alpha, then I would be referring to, and I insisted that this was not a function on the spacetime, then I'd be talking about a single vector space. But it's, for all of our work now, it's going to be implied, and even if I don't write it, and I probably won't write it, that this is a function on the spacetime and we're talking about a vector field. And this thing here, this object here, is the set of all vector fields on S. Okay, that's what we're talking about. So I can take any vector field on S and any vector field on S and create, say the first vector field is called X and the second vector field is called Y. That ordered pair XY is an element of chi S, Cartesian product chi S. And you guys know by now that I don't mind repeating myself and that this is sort of old news. So T is a function that takes an ordered pair, that takes an X and a Y, and it returns a Z. And in each of these cases, X is understood to be X alpha, a function on spacetime, partial alpha. Y is Y, call it beta, function on spacetime, partial beta. And Z is Z gamma, function on spacetime, partial gamma. And so in a normal textbook, these guys would probably be boldface, right? Sometimes you would, in an engineering book, you would have arrows on it, but we don't generally in physics use the arrow symbols, although I'm tempted to here because I can't easily do bold, and I'd like to. I'd like these to be boldface. So maybe I will throw on arrows. Okay, so that's what the torsion was. The torsion was a mapping that took two vector fields and returned a third vector field. And notice that that's not a tensor mapping, right? That's a tensor mapping takes a bunch of things and gives you an element of the field, which is the real or complex numbers. And in general relativity, it's usually or almost always the real numbers. I shouldn't say always, but it is usually the real numbers. It certainly is true for elementary and intermediate general relativity, that it's the real numbers. So we're going to proceed with the same kind of logic that we used with the torsion. We're going to define, make a definition, a formal definition of the curvature, and we're going to begin by working with that. Now the curvature is similarly defined as the torsion as a mapping, but the curvature takes an ordered triplet, a triplet of vector fields and returns a vector field. Well, the torsion took a doublet, an ordered pair of vector fields and returned a vector field. So, but the logic is going to be the same. We're going to have to create this kind of mapping and try to understand how we can get from that mapping into a tensor. Now in coordinate-free notation, this is our answer. I'll remind you that the torsion, which we already discussed in another lecture, in coordinate-free notation is the covariant derivative in the direction x of y. And I should point out that y is a vector field in this case, right? And then the coordinate derivative in the direction of y of the vector field x minus this commutator between x and y. So I like to play around with the coordinate-free notation and then translate it into the coordinate notation because that's sort of my thing. That's the way I like to do this presentation, is play around with the different notations. And it's more than just notation here, right? There's coordinate-free and the coordinate basis. It's important to understand those two distinctions. It's not just notations of the same idea where one book might use one type and the other book might use another type. You actually need to know both because there's different pieces of the theory that are best understood in this way, and certainly there are many pieces of the theory that are best understood when you dive into the coordinate basis. So let's break this one down. Let's remind ourselves how this breaks down into the coordinate basis. First, we'll take a look at the first term. Step one, if you want to do it in full detail, is you substitute the obvious coordinate expressions for the two vector fields that are relevant, in this case y and a. So we'll use alpha as the sum, the dummy variable for the x vector, and beta as the dummy variable for the y vector. And we'll leave this as the covariant derivative. Then the next step is to understand the linearity of this guy with respect to the its vector index here, and we pull out these terms out in front, and we leave behind the covariant derivative and just the basis vector down there with y and with leaving y in the way it was. Then we understand that this is a derivative object, but this guy, you can't take a derivative of it. So it just pops out, and the Leibniz rule would end up with a product, but one of them would be 0. So you just sort of group it this way. And this notation here, the covariant derivative in the direction of a basis vector, is just indicated with the index of the basis vector. We kind of eliminate that. It becomes, this is sort of the absurd subscript of a subscript problem. And it's very conventional just to eliminate that. So this symbol here literally means that symbol right there, which is the covariant derivative in the direction of the coordinate basis vector, basis alpha. And then the final step is to translate this object into a different, this is a purely notational step. This object, it's nicer to write it this way because now you see it as a 1-1 tensor component. So you get rid of this symbolism, and what we do is we do our double line here. But I will remind you that in most textbooks, it's a semicolon, all right? But, and then, as I've mentioned before in many of the other lectures, typically we do not even express the ultimate basis vector piece here. We just leave that off because it's sort of redundant. Whatever's left over has an implied basis vector. If it's an upper index that's left over, you end up with a basis vector that's a partial beta. If it was a lower index left over, it would be a dx beta. But the fact that the index is left over is completely enough to tell you that it is either a vector or a covector or some tensor, depending on the number of indices that's left over. Now, ironically, I've argued against doing this in my What is a Tensor lecture series, where I've brought these around all the time, but presumably you understand all that now. Now you're eligible to play around with this because you totally understand that there is a basis vector floating around. Okay, so that's we've taken this coordinate-free symbol and cast it through this process in a coordinate basis notation. So we can now do it the rest for these other guys. And there you have it for our breakdown. You'll notice that there's a lot of dummy indices. There's alpha is a dummy indice here, beta is a dummy indice here, alpha is a dummy indice here, beta is a dummy indice here. And understand that this commutator is defined this way, but there's this minus sign out in front as well. I didn't include those minus signs. So this is just the breakdown of each individual term. Now we can combine these terms together, but when we do that, we're going to try to give them all the same leftover index. In other words, here the leftover index is beta. Let's be sort of egalitarian here. We'll change that to delta. That we want the leftover indices always to be delta. Now we can always change the dummy indices arbitrarily. So let's change. We've got to get it so all the leftover indices are delta, so the final thing has one, in principle, partial delta at the very end of everything when we finally group it all together. And that final expression would look something like this. Notice that these are now single lines because, remember, this element here, this is going to be x alpha partial alpha acting on y beta. And so you'll end up with this derivative here is a regular derivative. So that becomes just y beta alpha like that. So it's a single line. And remember again, in normal textbooks, it would just be a single comma. It's just a little bit easier for me on this board to use lines, and I actually prefer the aesthetic of the lines as well. And then there's this implied vector basis out here. So that's how we broke down the torsion. And if you, since I can't resist reminding you, if you actually expand this in terms of the connection, what you'll discover is that this part and this part both have a regular partial derivative piece inside, which will cancel with those two, and all that will be left is the difference of the antisymmetric part of the connection will be all that's left, and that's the thing that we set to 0 in our earlier studies. So now we want to have a look at this guy in sort of the same analysis. First, let's understand that this definition that we're going to use for this mapping is in fact a vector in the end, right? And it should be easy to see from our breakdown of the covariant derivative in the direction y of the vector field z. Remember, these are all vector fields here. And the way we see that is, since we know that this piece here is going to be, say, y alpha z beta covariant alpha, like this, well, we see right away that this sums out and we're left with only a single contravariant index, which is indicative of a vector, right? There's the implied covariant covariant basis, right? The basis vector has got a covariant index on it. So with that, we know that whenever we take a covariant derivative of something, if we had just written covariant derivative of z, that would have given us z alpha beta, like this, with two lines here, which would have taken a vector, a 1, 0 tensor, and given us a 1, 1 tensor. But once we immediately contract that last index out by going in this direction of y, right, or I guess the way we would do it is like this, that we contract that away and we stay in the vector world. So this guy here is a vector. And once we know that this is a vector, then the covariant derivative in the direction x of a vector, well, we've just shown that the covariant derivative in the direction of a vector field is still a vector field. So this whole thing is going to be a vector, and likewise, for the same reason, this thing is going to be a vector. Now, this is going to be a vector too. This is the covariant derivative in the direction of the vector field x commutator y. But in our last screen, we just showed, we calculated this commutator, and it was this thing, which is a vector, right? So the commutator of these two vectors is a vector. So this is the covariant derivative in the direction of a vector of a vector. So this guy's a vector. So this, clearly, this whole thing is in fact a vector. All right, so we have this expression, which shows up and is actually can be manipulated into a couple different forms, and it should be easy to tell the forms apart. For example, you can just factor out the z, right, and then create something that looks like an operator that acts on a vector. So here the z is here, here, and here. You just sort of pull it out. That's one way of doing it. Also, this can be combined as such, right? This is simply a commutator of a covariant derivative in the direction of x and y, right? So we just write it that way, and that tightens it up. And these kind of forms are going to help us a little bit with understanding this thing intuitively in our upcoming lessons. But understand these forms are all the same thing. These two, however, are evocative of something that is commonly done, and that is to write this as r of x and y operating on z, where this is r x, r y. So this is now a mapping. Rxy is a mapping that takes two vectors and returns this object here, which is still another vector. So it takes two vectors and returns this thing here, which is a operator that operates on vectors to give other vectors. That is, it's a differential operator, essentially. So this is a very common form, and this is a very, very common form for this particular type of mapping. But now we understand, though, that in either case, whether the argument list is like this or like this, you're still taking three vectors and producing another vector. But our goal is to find a tensor out of all of this. So ultimately, if we use this to get a vector, in order to get a tensor, we have to take that vector and end up with a real number. And the way we're going to do that is we're essentially going to find one form or some covector and find the dual space mapping of that with the vector that we produce through this operation using this curvature mapping. This guy here is clearly an element of the real numbers. So this thing here actually acts as a tensor, and that's the curvature tensor. And the way the standard notation for the curvature tensor actually swaps out the z, x, and the y, and it's defined as this thing right here. It's defined as this guy. And so this is now our curvature tensor. So this takes four things. It takes a covector and three vectors, z, x, and y, and it produces the real number where you use the curvature mapping on x, y, and z, and you run it through whatever the covector is using the dual space mapping process, and this is always going to be a real number. And so this guy here is now a 1, 3 tensor. And we have just defined the 1, 3 tensor in coordinate-free notation. Specifically, we can actually write it down in great detail. For example, we could write it this way, where I'm now using I'm using this third form of expression, and I substitute right into our definition. And now we're getting something in coordinate-free notation, where we're expressing everything without any components, without any coordinate system. And I'm now using this notation of the commutator. I'm using it here and here both. And this is now the definition of the curvature tensor. It's a very abstract definition, because remember, I'm just starting with this. I'm telling you, oh, this is how we define the curvature mapping. I created this curvature mapping, and then I defined it using this thing. It kind of looks like, well, maybe we're forced to believe this. If you want a mapping that takes 3 vectors and returns a vector, and you want it somewhat anti-symmetric in x and in this part, but not completely, because you got to get this. Can you imagine other things? I don't know if this is forced on us or not, but we're going to work backwards after we understand this abstract form to understand where it actually comes from geometrically. But we're going to start, because I do things backwards, we're going to start with this formalism. So you're going to have to accept this, and then we're going to derive it systematically a little bit later. But once you have this, and all these three are equivalent, we can write down this tensor, right? And we use this convention where z is now first, right? So it was x, y, z here, or if we had used the other notation, it would have been x, y, z like this. But notice that in the tensor, the ordering is a little different, and that z comes up front. And that matters when we convert it to coordinates, which we're going to do in a moment. So let me move this up and now write down. Now I'm going to expand this out, and we're going to find the coordinate form of this, or the component form of our tensor. So the first step is to just sort of blow up this commutator and distribute the z, and you basically get this expression. I'm trying to put the order of operations, right? We're going to first execute this derivative and then that derivative. So I put in these parentheses here and here. And by the way, again, you can see, right? Remember, this is all going to still be a vector, right? We've already kind of gone through that. This is the directional derivative. This guy here is a vector. So it's the directional derivative in a direction of a vector, which is still a vector. But so that vector then dual space mapped with this one form, that gives you the real number. And the same is true for these two spots right in here. So now let's understand what this is. If we were to write this out in a coordinate basis, what would this guy look like? Well, the first thing we remember is that any tensor in a coordinate basis will have a component, which is a field, right? This component is a function on space-time. And this is the basis vector of the tensor product space relevant to a tensor, a 3-1 or a 1-3 tensor. Here's the 1 and here's the 3. So this guy here gobbles up 1 covector and 3 vectors. So that means it should gobble up, in our case, omega, z, x, and y. Right? So this is just a restatement of this expression here, where instead of r, I kind of wrote r out in component form after casting it in a particular coordinate system, the x mu coordinate system. And these components are what we're after. We want to figure out, what are these components? These are sort of unknown components, and they're what tell you how the machine works, right? Because these guys, each one of these vectors is going to be immediately substituted for omega alpha. Whoops, not alpha. We've already used alpha. Omega mu dx mu, and then this will be z. Let's see, gamma alpha mu nu partial nu, right? And likewise for x and y, and those will get substituted in here, and these components will be linear, so they'll just pop right out front. And but if you don't know what these are, you're never going to be able to crank out the value of the real number that this represents. Remember, this represents a real number. We got to calculate what these components are. So the way we calculate those components is actually pretty simple. I'm simply going to run the tensor against the basis vectors. These are all vectors, right? It's just they're constant vectors that are the basis vectors of our coordinate field system in our coordinate system. So if I can calculate this, that will end up being these real numbers. In other words, the value of this is this. So I pick, say, if mu equals 0, rho equals 1, nu equals 2, and eta equals 1, this is going to equal rho r0, 1, 2, 1, right? So I need to just be able to do this calculation. Let me eliminate those. And this calculation is going to be very simple. Let's just do it this way. I take this guy and I replace it with dx mu, comma, rho, partial rho, partial nu, partial eta. And then we operate each of these basis vectors on the arguments. And what are we left with? We're left with r, alpha, beta, gamma, delta, times the dual space mapping of dx mu partial alpha multiplied by the dual space mapping of dx beta partial rho multiplied by the dual space mapping of dx gamma partial nu multiplied by the dual space mapping of dx delta partial eta. And each of these, of course, is just a delta function. Mu alpha, this is delta beta rho, this is delta gamma nu, and this is delta eta, which ultimately means that this thing is going to be r mu rho nu eta, like that. And so that's the calculation, right? That's the calculation we have to do. So we have to now calculate this guy using this definition of things. And then we will ultimately have our coordinate expression for these components. All right, so now we want to find these components. Let's get this done. I want to take the curvature tensor of the basis vectors, but I want to apply this formula. So I have to substitute for x, I have to substitute dx mu. I'm sorry, for omega, I have to substitute dx mu, the one form. For x, I have to substitute the basis vector partial rho. No, I'm sorry. Partial rho is for z, right? For x, I have to do partial mu, and for y, I have to do partial eta. And that comes back to the fact that our definition is omega z x y, right? Equals omega r x y z, right? And that has to do with our definition, right? So to make this substitution here, I got to go step by step, but it shouldn't be hard. So let me begin. Okay, so we have this. Let me finish that up there. So this is a pretty straightforward application. Everywhere I see an x, I substitute partial nu. Everywhere I see a y, I substitute partial eta. Everywhere I see a z, I substitute partial rho. And you end up with this expression here. Now what's important to notice right away is this commutator, partial nu, partial eta, right? That's going to be d nu eta minus d eta d nu, which we know that these partials commute, so this guy is 0. So we can start right away. When we're looking for components, it will happen to be that that field is automatically 0 in the coordinate basis. In the coordinate basis. There are non-coordinate bases, by the way, where that's not true, where the non-coordinate basis vectors, these commutators do not cancel. But we're in the coordinate basis now, which is the only one we've really learned about, so that goes away. So why don't I actually just go ahead and erase it? Like so. So now we are left to analyze what's the remaining parts. Well, what's important is this guy here. That guy here we've actually seen before. We've seen it in this form, where instead of just leaving the index down there, I left the whole basis vector. Remember, if we're going to substitute, if we're going to go covariant derivative in the direction of y, our first substitution really is to replace y with partial eta. So that's partial eta. And then we make the notational simplification to just call that eta. So that's where these etas come from through this. So it goes from y to partial eta to just eta. So this is all to be understood as the same thing, right? This is the same thing. It's notationally, it's just a mere notational difference. So with that in mind, we've seen this object before. That object is literally the definition of the connection coefficient. So the connection coefficient, this is a vector now, but the actual vector that it is its component is the connection coefficient. And you have to kind of go back to our differential geometry stuff since it's probably been a while, but you'll see that this guy here is defined as this guy. And remember, everything works, right? This is a vector. This is the covariant derivative in the direction of another unit vector, so this is a basis vector, and this is the covariant derivative in the direction of a different basis vector. And the covariant derivative of a basis vector in the direction of a basis vector is defined as the connection coefficient. You can't really simplify this. This has to be given on your space-time. As I've said before, the connection coefficients are arbitrary. And although the whole point of general relativity in some sense is to seek what is nature's choice for these, the fact is that mathematically this is the arbitrary thing. This is like the smallest little element you can get in your differential geometry analysis of a space-time. And so we just give it a name, and it's the connection coefficient. Notice that the connection coefficients indices are reverse, right? So you have rho eta like this, and you swap them. You get rho first and eta second. That seems to be a convention as well. But anyway, the point is that this becomes this vector right here. So let's make that replacement. And here we have that substitution. And so now we are looking at taking these, executing this covariant derivative. This is now a regular covariant derivative. I guess what we could say is the covariant derivative in the direction of a basis vector. That's simply the covariant derivative. And so we're now going to take the covariant derivative of this term and the covariant derivative of that term. And in order to do that, we have to remember what our actual definition of a covariant derivative was. Remember, this is a covariant derivative of a vector, right? Because this is a real number, and this, with that basis vector here, makes this object a vector. So we're now taking the regular covariant derivative of a vector. So that definition of the covariant derivative is this guy right here, which we learned previously. This I meant this to be in very general terms, but the covariant derivative of a vector x sub mu is given by this expression, which involves the normal derivative and this correction term in terms of the connection. And we've derived this before. I guess I should make it clear that this is actually also written x nu double bar mu equals x nu single bar mu plus the connection b mu x beta, like that. So now we take this guy and we work our substitutions up above, where this x mu gets replaced by rho nu partial sigma, right? So we've got to understand all of the kind of crazy notational issues that we're doing here. This is your pure component notation, where we don't trail around any basis vectors. If we did trail around a basis vector, this thing would look like this, x nu, and then it would be partial nu tensor product dx mu, like that. Which is strange because the ordering here is not the same as the ordering here, which is supposed to be the rule, right? So that's why they invented this notation, right? So now the ordering on this thing is the same as the ordering there. But we leave that off, and then we end up with this expression. But this guy here is the equivalent of not leaving it off for the vector. So you would write this vector, if you were to write this vector x nu partial nu instead of just x nu in the pure component form, then this x nu would actually be this term right here, this which is a function on spacetime, right? This connection coefficient. So maybe it's a little clearer if I write it this way. If I distribute away or factor out the partial sigma to here, and then we leave this term here. Now we're talking about the covariant derivative of a vector whose component is given by this connection coefficient. So because this is not a tensor, right, we're not talking about the covariant derivative of a tensor. You're actually talking about the covariant derivative of what amounts to be a vector. And this rho and nu are just coefficients that sort of identify what vector it is. So let's make that substitution, right? Let's make, using this rubric, make that substitution in here. And I think this is pretty much the substitution. So I've replaced this and this with the terms that it would share if we used this little rubric down here. And then the last step is to just exercise the dual space mapping, which this is simply a number. Remember, this is a function. These are functions on the spacetime, so it's a real function. So that just pops out front, and you're left with dx mu partial sigma delta, which is a delta function of mu to sigma. So all of these sigmas become mu's, and then we have our final result, which I'll write down here. Let me go ahead and clear it. And there you have the final answer for the components. And so now we've created this object called the Riemann tensor. And now in that we know the components of the Riemann tensor, we know how to create it as a tensor, where the rule is now straightforward. The non-coordinate object is equal to, and we can now express it in terms of a coordinate object. These guys here are now known through this expression. And this expression is known because we assume that if we're dealing with a space-time, if we're dealing with an actual space-time that's got coordinates, and our space-times always do because it is an assumption of the theory that space-time is a four-dimensional manifold, and because it's a manifold, by definition, it has to have coordinates. And every point in that space-time is labeled by the coordinates. At every point, we have our little vector space and our dual space and all the tensor product spaces. But it's a 4D manifold, and we presume it's got differential geometry operating on it, which means there is a connection defined everywhere on the manifold as a function of the coordinates. And that's what all of these are, right? All of these are functions of the coordinates. These are all functions of the coordinates here. And I'll take those out because we don't usually write that they're functions of the coordinates because everybody knows. So this is presumed to be given, right? This is presumed to be given if we really understand our space-time. So once we've given these functions, we can take these derivatives and we can make these products and we can end up getting the tensor. So the Riemann tensor is directly constructed out of the connection. In fact, the thing to remember is everything is constructed out of a connection. This is the ultimate geometric object in a sense. Everything goes back to the connection. And the connection, remember, the connection always goes back to the metric. So ultimately, everything goes back to the metric. And that's an important thing to always just keep that in mind, just to sort of remember, how does this all walk back to the metric? Okay, so this is the definition of the Riemann tensor in terms of the coordinate basis. And let's see how we got to this spot, and we'll review it and then call it a lesson. So we began by the abstract definition of the curvature, which was a mapping from three vectors to a vector. And then we kind of renamed this thing xy operating on z. So rxy is a differential operator operating on z. But it was still defined the same way. Although in that notation, it's a little bit cleaner to write it in this sort of in this form that involves the commutators in both places. Okay, so that's where we started. And then we remembered a few little facts that were important. For example, the covariant derivative of a basis vector, right, was in fact another vector. And using that fact and a few other little facts, we were able to calculate the components of the Riemann tensor. We were able to define a Riemann tensor and then calculate its components. This was how we define the Riemann tensor, which is now an object that takes one covector and three vectors and produces a real number. Remember, this guy here produced a vector, and this is a covector, and the dual space mapping of a covector on a vector is a number. So this is our Riemann tensor in the abstract form. Then using the definition here, we substituted in here, and we evaluated the following. And this expression was simply this expression here with this following substitutions. And we know that this is actually the components of our object, of our tensor, of our 1,3 tensor in the coordinate basis. And then ultimately we calculated the value of these components in the coordinate basis in terms of the connection. Now in principle we could go a step further and we could take each of these connections and we could calculate them all in terms of the metric. So let's see, I guess I would have to name the metric alpha beta. And then this thing here would be in terms of, now we know that the connection coefficient depends on the first derivatives of the metric. Say I throw in a delta here. But this guy here, the Riemann tensor, depends on the first derivatives of the connection. So it's going to depend on, say, the second derivatives of the metric, right? So it's going to depend on the second derivatives of the metric, the Riemann tensor is, which is interesting. So in the next lesson, we will start sort of exploring the Riemann tensor from different perspectives. This was the formal perspective, where we literally start with the mathematical definition of a mapping, of a particular mapping, and from that particular mapping, we ended up with a true tensor. Remember, somewhere along the way, we proved linearity of this guy, which was important because this whole thing has to be linear. If it's not, then this will never be a tensor. So we showed that this was linear, and of course dual space mappings are linear by definition, and so our Riemann tensor is going to be linear. And ultimately we were finished up with this expression of the Riemann tensor in terms of the connection. And now in the next lesson we'll start peeling this apart and gaining a little more geometric insight into this object.